Hi, everyone. Today we have Professor Papamanthou as our speaker. He's a professor at UMD now, and he's joining Yale this year. Today, he's going to talk about his work, Leakage Abuse Attacks in Encrypted Databases. Let's welcome him.
Okay. Thank you very much, Kay, and thank you very much for having me today. I'm very excited to give the talk here. So today I'm going to talk about some work that I've been doing for the last two or 3 years, I would say, on leakage abuse attacks in encrypted databases. So the talk outline is as follows. First, I'm going to talk about what are encrypted databases and leakage attacks. Let me minimize this. Okay. And then I'm going to talk about a simple attack on range search leakage. Then I'm going to talk about, this is not our work, this is just to motivate the problem. Then I'm going to introduce a distribution-agnostic attack for the same problem. So this is work that appeared in the IEEE Security and Privacy Conference in 2020. And then I'm going to suggest some new directions that we're looking currently to work on that I think are very promising. Okay, so let's go right into it. For some reason my entry doesn't work, so I have to do with it. Okay, so what are encrypted databases and leakage attacks? So what is an encrypted database? An encrypted database okay, so an encrypted database is a database that is encrypted, of course. So let me tell you how the protocol works. You start with a plain text database that you have on your laptop. And because of storage purposes, you don't want to keep storing the database on your laptop. So what are you going to do? So you're going to ship the plain text database to the cloud, right? And you're going to do that in an encrypted format. Okay, that's why this database turned into this squares. Okay, now the question is that you have achieved very good privacy because the database is encrypted, but unfortunately, you cannot perform any queries on database anymore because the database is fully encrypted. An encrypted database addresses this problem. In particular, it provides an encrypted index on top of the encrypted database that allows the client to still perform a subset of queries on the database that was able to perform when the database was in plain text. So let me give you an example. So for example, what would happen here is the client can send now an encrypted join, an encrypted select, and an encrypted range query. These are encrypted using to interface to interact appropriately with the encrypted index, right? And then using the encrypted index, the server can actually pick which encrypted records match these encrypted queries, okay, without ever decrypting the records. And all this done using this notion of encrypted index. Okay, so there has been a rich literature on encrypted databases, right? So it started with the work of Don Song in 2000, David Wagner and Andrew Perry. So they proposed this notion of searchable encryption, where it is the most fundamental version of an encrypted database where you want to support just search queries. So give me the set of records that match a specific keyword, okay? And if you just do a scroller on databases, you get around 7,000 results. So it's a very active research area, okay? And we've been working in my lab for a long time on encrypted databases. We have around 10 papers, and one PhD thesis was written on encrypted databases in my lab. And typically how you implement them, it's not rocket science. You kind of use some sort of hash tables, but with encrypted keys. And the main important thing to remember about encrypted databases is that are extremely fast, right? So they're very fast compared to other approaches that provide some sort of encrypted computation on encrypted data, okay? So for example, if you compare it with other solutions like FHE and ORAM, encrypted databases are extremely fast, right? You're getting like a 10x or a 20x overhead gaining at the server, okay? Now, of course, all this sounds good. So you can have an encrypted database and you can perform encrypted queries, but of course, there has to be a trade-off, right? There's no free lunch, right? So the caveat here is that there is leakage, okay? So what is leakage? So leakage is some information that we're okay with leaking when we're using encrypted databases. Okay, so we decide, okay, since I want to have an efficient encrypted database, I'm gonna agree that it is okay to leak some information that, from a first sight, it looks harmless. Okay, what kind of information is that? Right. So first of all, encrypted databases leak which encrypted records match the query. Again, you're not leaking the plain text records, but you're leaking which encrypted records match the query. Well, why this can be harmful? Well, this can be harmful because if you have two different queries and they're returning some common records that are encrypted, then this could be catastrophic information, right? This could help you decrypt something. Okay, but this is what is being leaked right now in encrypted database. And I think this is one of the main reasons why they're so fast, right? Now, in terms of search pattern, this other kind of leakage means that you are leaking whether a query has been observed before. So for example, if I do a range query, an encrypted range query, now to like at 10 o'clock in the morning, and I do the same encrypted range query at 5 p.m., the adversary that is sitting there and observing the queries that are coming in will be able to tell whether these queries were exactly the same. Okay, in other words, the queries are deterministic. Okay, so I'd like to do a pause here and answer any questions, if there are any questions, because it is important to understand the background so to continue for the rest of the talks. Are there any questions on what an encrypted database is and what is the leakage in encrypted database? Okay, I'm guessing there are questions. Okay, so let's continue. Now, because of this leakage, people have asked the question, right? It seems harmless from a first sight, but wait a minute. Maybe you can exploit this leakage and you can actually decrypt the underlying plain text database by just observing this leakage. And indeed, this is something that started with some work in 2008, I think, and then there was a seminal paper around 2015 that looked into range search attacks. This is the paper by I don't have it here, but it was by Kelaris and others. Kelaris convinced him that they looked into how you can attack leakage for range search queries in particular. And then this specific paper kind of launched a whole area of trying to see how harmful is this leakage on encrypted database. And should we be using them? At least, when we're using them, we need to be very clear what are the trade-offs are, right? And if we're using a database, you need to understand what the attacks are, and so that you know exactly what kind of security properties you're getting, right? So the main question that this attack has is, given access to the leakage that I described before, in particular, given access to the search pattern and the access pattern, what can we infer about the plaintext database? Okay, right. And so this talk is going to be about how to exploit leakage from encrypted range queries. Okay, so in particular, you have a database that you have encrypted. You have this encrypted index that allows you to answer encrypted range queries. Now, every encrypted range queries that comes in leaks to the adversary which encrypted records match the encrypted range query, and also we leak the frequency of the same queries, right? So if there is a query that is being repeated, this is also being leaked. Okay, so this talk is going to be specifically about range queries. Okay, so let me continue. Okay, so let me start with a very simple attack on range search leakage, right? And please feel free to interrupt me if there's something that is not clear. Okay, so I will try to go a bit slower here. Okay, so now let's see what kind of setting we have. So we have an encrypted database over domain 1, n. In other words, the searchable attribute takes value from 1 to n. Okay, and the setting is that the adversary observes uniform range queries over the domain 1, n, right? So there is range queries, which is basically A, B, and there's n squared of them, and there is a client that issues uniformly distributed range queries over this domain. Is it clear? And what I mean by observing uniform range queries is that the adversary observes the leakage that comes out of this uniform range queries. Okay, good. So let me give you an example here. So for n equals 200, this is the domain of the database. You can have database records whose values are 15, 27, 56, 57, and so on and so forth. So I'm showing here exactly 10 database records, right? And the letters underneath are just the identifiers of this database records. So X, Z, A, T, F, right? So you can view this as like, kind of like pointers, right? Just identifiers, like the name of the record, right? Okay. Now, the reason I'm having this net on top of the numbers is that I want to indicate that these records are not plain text, these are encrypted records. So this 15 lies under a semantically secure encryption scheme. Okay, so these are all encrypted databases, and what the adversary just sees is this random identifiers X, Z, A, T, F, R, Y, W, Y, and O. Okay, is it clear, the setting? Good. So let's see what happens now. So if the client sends a query, give me the records that fall into the range 1188. So basically, this is an encrypted range query. Now the encrypted database will return X, Z, and A. In particular, it will return the identifiers whose corresponding encrypted records fall into this domain, right? Again, I'm not going to tell you how this works because it's not the focus of this talk, but believe me, there are schemes that can work in this way, right? Okay, so you can return the encrypted records that fall into the encrypted range. Okay, so now if there's another query, encrypted 28100, right? So what's going to happen here is you're going to return A, T, F, and R. Again, the identifiers of the records that fall into this range. Okay. Now, the question is now, if you're seeing this access pattern leakage, right? What can we infer about the order of this record? Is there something that you can infer about the orders of the records? So say you're seeing a bunch of encrypted range queries returning this set of identifiers. Can you somehow try to order this set of records? Because this set of records are not returned in a specific order, right? So I have them here in a specific order, but the server can kind of mix and match, right? So I'm not going to tell you the whole algorithm how you reconstruct the order. I'm going to just give you the intuition, right? So the first step that the attack will do, again, now the goal of the attacker is to, by observing these identifiers, to figure out the actual values, 15, 27, 56, like what are the actual values, right? So let me describe you a very simple attack. So the first step that the attacker is going to do is going to be the order reconstruction. Right? We're going to give you the full algorithm, but here's intuition, right? So can you reconstruct the order of the records that are returned? The intuition is that if I see a pair of records, in other words, if an encrypted query returns exactly two records, they have to be adjacent, right? Because it's a range query, right? So if there was something in between, because it is a range query, it will have to be returned. Okay, so this is the main intuition. Right. So how do we use this intuition to actually reconstruct the order? Imagine a scenario where the client issues queries that return exactly two records, all of them, right? And then the adversary observes the access pattern. So let's see this example. So the first query issued by the client returns exactly two records. This is XZ. Now, they have to be adjacent because it's a range query, okay? Now, the second range query that the client issues happens to return Z and A. They have to be adjacent Z and A, and so on and so forth, AT. And in the end, you're able to reconstruct this order up to reflection, of course. Okay, so you know that X is less than Z, less than A, less than T, up to reflection. Is it clear how this simple example works? Right, so again, I'm not reconstructing now the actual values of X, Z, A, and T. I'm reconstructing the order because I have this property that every answer that contains exactly two records has to be adjacent because of the property of the range query. Good.
Sorry, I have a question. So, so while we know the orders, can we also know the range of X from the queries?
The range of X, you mean?
Or Z. Let's say the query is 811 or 1118, and I know that 11 is between X and Z, and 18 is between Z and A. So basically, Z is between 11 and 18. Is that correct?
I don't know the plain text query. So maybe that was not clear. So the plain text query, I don't know. I just see an encrypted query that returns X, Z. Then I see another encrypted query that returns Z, A, right?
I see. That makes sense. Thank you.
So remember here, I mentioned encrypted 11. So the queries come encrypted. Okay?
I see.
Okay. Good. Yeah, thanks for the question. Okay. So, right. So the first step is to reconstruct the order. So assume, if you see enough queries, then you can reconstruct the order, right? So, but now, reconstruct the order is not enough, right? You need to have the exact values. What do this element represent, right? So the value reconstruction works as follows, right? So imagine you have the domain here from 0 to 200, right? And there is these dots, these red dots indicate the values of the encrypted records, okay, that I'm having in my database, right? Now, the main observation is the following. So if we assume a value V is contained in the database, right? Let's ask the question, what is the probability a uniform query Q will return V? Right? Remember, we have an adversary that observes uniform queries from all the possible range queries. Again, they're n squared, capital N squared range queries. So what is the probability a uniform query Q will return V? So, the intuition here is it is large for V that is in the middle, because there are many range queries that cover the middle point. And it's much, much smaller for elements that it is in the edges, right? So this already kind of gives you a way to distinguish and get information about the values by just observing uniformly distributed queries. In particular, how many queries return a specific encrypted record. Okay, so this will give you, right? So let's compute this probability. The probability V, a uniform query Q will return V, is the sum of Q in RV of probability of Q. Probability of Q, it's 1 over n squared, right? It's uniform, right? And calligraphic RV is the set of queries that return a specific value, right? So for example, calligraphic R0, how many is that? It's exactly, it contains how many queries? It contains 0, 0, it contains 0, 1, 0, 2, 0, 2, 0 to 100. So it's around 200 queries, okay? So now, the thing is, even without observing any queries of the adversary, of the client, we can compute this probability. We can compute this probability table that gives you exactly a specific value for every query, for every value, assuming the queries are uniform, right? So this is what we're going to do. So the algorithm works as follows, right? So we're going to compute this PV for all values of the domain, right? So this is, if you compute it, this comes out as this nice curve. So this is parabola, right? And again, the reason the probability is bigger for 100 is that because there are many more range queries that return this 100, right? And this is the value you get. And now the algorithm decrypt is simple, right? So you're sitting there, you're observing a bunch of range queries, right? So observe few uniform queries, and then you first reconstruct the order of the records, and now how you go about to reconstruct the value? Well, for each return record X, compute QX, how many queries in Q contain X, right? And find V such that PV is closest to QX over Q, and break types based on order, right? And then you decrypt X to V. Right. So again, the algorithm will take an input, this table, probability table, right, for every value of the domain. The adversary sits back, observes the range queries, right? And then computes the empirical frequency and matches the empirical frequency to the theoretical frequency, and then makes a decision. Okay, probably if I'm seeing this record being returned all the time, right? Probably this record has to be 100, right, or close to 100. Okay, so this is a very simple attack. Okay, for encrypting, for deciding the values. Any questions so far? Excellent. Good. Now, of course, if we look at this attack, one of the very, very important assumptions that this attack made was the fact that the probability of the range queries was uniform, right? Unfortunately, this is not the case in the real world, and here's where our work is coming to play, right? So in the real world, if you think about Google Maps, for example, the probability of making a query, on a river, right, is very small. Actually, it's almost zero. The probability of making like a query, like downtown, Pittsburgh is much bigger, right? So from a practical perspective, you cannot really assume that the probability distribution of the queries that are coming in is uniform. Unfortunately, most of the work, right, that we have seen so far makes this assumption because it's a convenient assumption that helps the attacks in many ways. Okay, so this is actually our work, right? So let me give you an example why this specific approach that we talked about will not work under other distribution, right? So here I'm showing the probability table, right, underneath of the probability of a range query being A, B is not uniform, right? The query is not chosen uniform, but it's proportional to this quantity here, right? So it's an artificial distribution that we came up with, right? It's only so we did exactly the same, and here is how the probability table looks. So the problem with this is that if you use the same approach, you're going to be having a lot of values having exactly the same probability value, right? And then as you observe the queries, it's going to be very difficult to distinguish between V1 and V2 that happen to have exactly the same probability in this table. So that's why this approach that I just talked to you about works only for specific probability distributions. It works actually very well for uniform probability distributions, but for arbitrary, it will fail completely, right? So we're trying to think about this problem, and this is our work. It's this distribution agnostic attack that we propose in October 2020, right? So this is joint work with Evgenius and Roberto, and so our work departs from this notion of computing these probability tables. So it introduces completely new techniques, and one thing that it does on top of everything is that it leverages the search pattern leakage and access pattern leakage. So the previous attack did not leverage at all the search pattern leakage, but it is always there, right? It is part of an encrypted database, right? So we're gonna take into account the search pattern leakage, and you'll see how we're able to have an attack for arbitrary query distributions, right? We don't know anything about the query distribution, right? For the range search problem. And this is what I'm going to talk for the rest. I'm going to talk about for the rest of the talk. Any questions so far? Okay, good. Okay, so the main insight is as follows. So suppose I have reconstructed the order as before, right? So say we have Z, A, T, and F. These are the identifiers of the encrypted records, and I want to figure out what is their values under an arbitrary query distribution. I have no clue what the query distribution is. Okay, now the idea is I'm going to ask the following question. How many range queries return the records A, T? Okay, let's start to think about it. How many queries return the records A, T together? Well, if you think about here are 3 queries that return the records A, T, right? So the intuition is both the left end and the right end need to be in this space between Z and A and between T and F. Okay, to return exactly A, T. Okay, so and this is exactly the distance between Z and A times the distance between T and F. Is this clear? So here is a connection basically between the number of queries returned a comma t with the distances of two different adjacent records. Okay. So the suggestion we have is wait to see all possible queries, right? And set up three equations. Okay. So this is a way to solve the problem actually. So if you see all possible range queries, right? Then you can say, okay, distance z comma a equal times distance t comma f is the number of queries that return a comma t, right? Distance t comma f is the number of queries that return z a t, and distance at is the number of queries that return tf. Okay, so you can actually set these equations, right? And if you know now NAT, NZAT, and NTF, then you can solve the system and you can figure out what the distances are. Once you figure what the distances are, then exactly you're figuring out what is the value of Z, what is the value of A, what is the value of T, what is the value of F. So this is basically the main intuition of our attack. Any questions here?
So this is based on all, like if the queries are from arbitrary distribution, then this computation is based on the observed queries.
Right. So exactly. So here I'm making an assumption again. I haven't talked about arbitrary distribution. I'm making an assumption. Say I have seen all possible queries, right? So if I see all possible queries, I will know exactly what NAT is, right?
Yes.
Right. So I can set up. So this works. What I said here, when I have the precise value for NAT, which is not the case as you just implied, right?
Mm-hmm.
So let's see what happens in the real world now when the queries come from an arbitrary distribution. Okay.
Okay.
So now, of course, if adversary sees all possible queries that return R, we will be okay. But unfortunately, in the real world, this doesn't happen, right? So this is the problem that we had to solve here, right? So what happens really is the adversary sees samples of queries Q that return a specific R. That's it, right? And then, so here's what happens. For a specific response R, you can have three queries Q1 that return it. You can have three. What I mean here is the following. You can observe Q1 three times, the same query, and returns R. You can observe Q2 two times, it's the same query and returns R. You can observe Q4 one time and returns R, Q3 two times and returns R. So in a sense, this is what the adversary says. Is it clear here what's going on? So these are the queries that return R, and these are the frequencies of the queries, because in the real world, you might issue the same query over and over again if it comes from an arbitrary distribution. Okay, so now the question is, if you see a sample of this, could you potentially figure out what is the total number of queries that will return R? So this is the main question, right? Can we estimate the total number of distinct queries that return R? Here we have seen only Q1, Q2, Q4, Q3, only 4 distinct queries that return R. Each one is repeated 3, 2, 1, 2 times. But the question is, how do we figure out the total number of distinct queries that return R? So this is the main question. Once we estimate this, then we can go back and plug this estimation to our original approach and hopefully get some results there. So let's see how we're going to do it. So to estimate the total number of queries returning R, here's what we're going to do. So we build up these towers, right? Q1 returns R has been observed 3 times, Q2 returns R has been observed 2 times, and so on and so forth. This is the input to the adversary, right? Now what we're going to do, so we build this table, and now recall that to build this, we need the search pattern leakage. So this is where the search pattern leakage comes from, right? Now we're going to use this notion of jackknife estimator that actually allows you, if you have this table of frequencies, allows you to estimate the support size of the distribution. Support size of the distribution meaning how many potential values the distribution has, right? That could return R, right? So we're using the jackknife estimator. This is well-known techniques from the statistics community. right? So that was not our distribution, our contribution actually to develop an estimator. We just used one that existed, and eventually we compute the total, we estimate the total number of distinct queries that return R. Okay, so this is basically how our approach works. Okay, so now what's the final system of equations to be solved, right? Recall that in the beginning, if you had the precise number NAT, then you could solve this equation, and then you could put precise numbers for D, ZA, and DTF, right? So now what you have is a VAT. So the red V is an estimation of NAT, which we get from running the jackknife estimator on the samples that we observe. Okay. And now how are we going to solve it, right? So because these are estimations, it's an optimization problem, really. So you have to set up an optimization problem. So minimize DZA, DAT, DTF, greater or equal than 0. And we set up these equations with this optimization problem, right? Now, the problem here is, no, actually, so the W's here are very important. We also put weight in front of every term of this optimization function to indicate how much confidence we have in the specific estimation of VAT, right? So if you have seen a lot of queries for AT, right? So then we have kind of good confidence on the value of this estimation. So this W is going to be adjusted appropriately in our optimization problem, right? So it turns out that actually how to solve this optimization problem, we could have used the package, but actually we're able to solve it analytically in the following sense. So instead of having this form, what we did is we took the logarithm of DZA times DTF, and we wrote this function here as log DZA plus log DTF minus log VAT. So our kind of unknowns are not the DZAs right now, are the logs of the DZAs, right? So this means that logs can take any value they want, right? So we didn't have any constraints. So actually we're able to take derivatives and solve this problem analytically for the logs. Okay, and then after we solved the logs, then we had to take them down to convert them back to distance. And it looks like this was a very good way to solve this problem. At least in the experiments, it has some good results. So that is exactly what we did. So let me recap the attack. So the step 0 is to reconstruct the order, right? So step 1 is to partition the queries based on return response. Step 2, compute frequencies within its partition. Again, the frequencies are very important for the jackknife estimator. Then you compute estimation of number of queries that return the specific response. You plug estimations into optimization problem, and then you output the distances and reconstruct the database. Right? And this is the pseudocode of the attack, where we actually solving this system of linear equations boils down into actually solving a linear system. Okay. Right. So
Professor, can I ask a question?
Yes.
Can you just go back to the previous slide? So I got confused. What is the difference between n and the one where you showed n and v, those equations?
Here.
So yeah. So n is the n of a comma t represents the number of queries that will have value, that will return the records a and t, right?
So NAT is the number of queries out of the total number of range queries, right? So that
total number of range queries that will ever be queried.
Right, exactly. So given a domain from 1 to n, you can write down all possible range queries that you have, right?
Yeah.
So in a theoretically, if you could see all possible range queries on this specific database, how many of them will return a comma t?
I see. And what does v of a comma t represent? How many did I see?
T is now, right, so the left world is like the theoretical world, right? But the right world is the practical, or what happens in practice. In practice, you have no guarantee that you're going to see all possible queries, right? In practice, you see queries coming out of distribution. So VA comma T is just an estimation of NAT given what you have observed so far.
Got it. And can you just say again, how did you use the search pattern leakage on the slide before this? I think I didn't.
Right. So say you want to estimate the total number of queries that return a specific response R, okay? Like A comma T, right? How many queries return A comma T, right? So now, as an adversary, you're sitting there and you're observing that there was a query Q1 that was issued 3 times and returned the response R, right? There was another query Q2 that issued 2 times and returned the specific response R. And there was another query Q4 that was issued 1 time, returned the specific response R. And there was another Q3 2 times that returned the specific response R. Is it clear?
Yeah. That part is clear.
Right. And now you take this, you plug it into a jackknife estimator that's distribution agnostic, and this technique outputs an estimation of the support size of this distribution, right? And the support size is exactly how many potentially other queries could return R.
Right. But I intuitively, where is the search pattern getting leakage? It is under this estimator.
Exactly. Right here, right? Because Q1, how do you know that?
This is the search pattern.
Right, exactly.
Oh, got it. Thank you.
Is it clear?
Yeah. And one more question. So on the next slide, where you had written that optimization equation, what are those W, AT, W? So those are just some optimization parameters that you have introduced.
So these are weights that I mentioned it before. These are weights that refer to how much confidence we have to this estimation of VAT, right? Because not all VATs are made equal, right? You might do an estimation of VAT after you have observed the big sample because of distribution, right? So these, you want to give it more confidence, right? So we basically use these weights, okay? Is it clear?
Yes. Thank you.
Okay, good. Okay. So these are some results. So here we compare on the uniform query distribution, right? So our thing is distribution agnostic, right? So it should perform on the uniform query distribution as well. So with the blue line, we plot the mean square error of the first attack that I described to you. Remember the one where the uniform distribution, use the uniform distribution and you're building this table, right? And then on the second one, we use our distribution agnostic attack, right? We don't build any probability table, but we just do exactly what we did. And as you can see, even from uniform distribution, as you can see that, you know, our approach performs better for certain parameters, particularly as the database grows beyond 20%, right? So the database density, meaning, you know, as you put more records in database, then we can see that our attack here performs better. Okay, and here we also have a bunch of you know, we also tried our attack on various distributions, and here I'm just showing some results on some different distributions. So what are the distributions here, right? So the colored points indicate higher probability of actually issuing this range. Okay. Right, so this is exactly the lower boundary and the upper boundary, right? So every point has a color that indicates the probability of issuing this range query. You can think of the uniform distribution as all the points in the grid have the same color, right? But here we tested this probability, I mean, kind of artificial distributions, and here we saw some results. Again, we were able to reconstruct databases with not that bad of an error. So here you can see like the mean squared error, right? And again, as the database density increases, we can see that our attack works much better. Okay. Okay, so to conclude the talk, I would like to talk a little bit about the field in general. So I would like to talk about you know, this is a big problem, right? So encrypted databases are being used. There are attacks out there. They're very powerful attacks. And, you know, it's not clear whether we should go along this way, right? But one question I would like to answer is, you know, even if we decide to go along this way with the encrypted database, at least we should try to have a formal understanding of what it means to leak certain information, right? So right now, what happens is we just say, my encrypted database leaks the access pattern and the search pattern, and that's it. However, you don't really understand what this means mathematically, right? And this is something that we're looking right now in our current project. So the idea is to introduce the notion of reconstruction space, right? Again, up to now, encrypted database leaks only access pattern and search pattern, right? But what we should be focusing on is we need to argue about reconstruction space, right? So let me give you an example. Imagine you start from an initial database, D, right? And then you issue all possible queries on this database, right? So every query is going to give you some leakage. So you take all leakage, L1 through LK, right? And now you ask me a question. Given this leakage, L1 through LK, how many databases could I have started from? In a sense, this kind of gives you a notion of security for the scheme. Why? Because if these leakage indicate that it's only one database that you could have started from, right? Mathematically, right? So that means that it's a really bad security. This has really bad security because you can go back from the leakage. It's a function that takes you back from the leakage to the database. But if you can argue formally that there's a bunch of databases that you can have started with, then the security becomes better. So let me give you an example. So for example, we know that for range search, the reconstruction space is exactly 2. And this is really, really insecure. In other words, if you have a range scheme and you observe all possible queries on the range scheme, now you can prove mathematically that out of this leakage, you can go back to exactly 2 databases, right? And this is very, very insecure. So the question is, how can we change the construction of encrypted databases so that to increase the size of the reconstruction space, provably, so we're able to prove that this construction will give you a bunch of databases that it's an increased space, and even if you see the leakage, you will not be able to tell which one you started from. So this will kind of provide a basis for actually arguing about how secure these things are. Okay. So any questions here? Okay, so I guess this concludes my talk. I'd like this work was done with my collaborators from Evgenios from Berkeley, Roberta from Brown, Alex from Purdue, and Don Song from Berkeley. It was a lot of fun collaborating with all these folks. And right, so yeah, that's it. Thank you very much. And I'll be up for answering any questions you might have.
Thank you. So I have a question. I want to ask why so for the optimization, you replace the original formula with a logarithm on it.
Right.
So why is logarithm better than the original formula?
Yes. So we tried to solve the problem with an optimization package, and it was cumbersome. So it was difficult to run this problem. It will take forever to finish. So let me go to the optimization problem. And so that was a way for us to actually solve the problem, right? Because if you had a lot of big databases, this just will never end. And so we kind of thought about this, and and we're able to produce an analytical solution. However, keep in mind that we're not experts in optimization. So it might be the case that there is another way to solve it much better without doing this. But this is what worked at the point, and we kind of did it, and it seemed okay. But it might be the case that if you talk to a very good optimization person, who might tell you, look, you might be able to solve it differently and in a much better way.
I see. Thank you.
Hi, I have a question. I was wondering about the runtime of this and how big the database was when you tested it, because it's growing exponentially with the size of the database, right? The runtime.
No, I don't. Why is it growing exponentially?
Or it's because your tests are not exponentially, but like n cubed, right?
Not n cubed. I mean, we have to solve the system, which I guess right.
But
Right,
you're testing it with like all like n choose 3 or n choose 3 combinations of the like if you go back to that
let's go back. So where exactly?
Here where you're trying to find the minimum of the
Right.
the 3 things, right? You're testing it with all n choose 3 combinations of those, or
It's basically no. So we're doing it for a linear number of pairs, right? So you don't have to do for all possible set of responses, right?
oh right.
So
Okay.
so for example, right? So it depends, right? I mean, if you for example, if you do it for pairs, sometimes it's enough. But the question is, will you ever see the pairs, right? So the idea is we left the queries coming out from a distribution, right? And we will judge which pairs of points or like triplets of points we will pick, right? But at some point we couldn't pick them all, right? So we will make a decision. Okay, we're gonna focus on this specific points, right? And in particular, because your unknowns here are only linear number of unknowns, right? Because you have the unknowns here are linear in the number of the points in the database, right? Because it's the distances between the points, right? So it was enough to consider a linear number of estimations, approximately.
Okay, that makes sense.
Thank you. Thanks for the question.
Professor, I have a question. So in the last thing you mentioned, that was very interesting, the mathematically working out the reconstruction space. Can you just say you already, I mean, can we do that? Like you said, it's a work in progress, but like it's doable is what you're saying.
Right. Yes, of course. So we have a construction where we're using padding and other ways to kind of conceal the result size, for example. So there's bucketing, padding, there's various techniques. And then we're able to mathematically prove that the size of the reconstruction space increases. So we have a result on that. So it's under submission right now. Actually, we do work on that, right?
And then what about other kind of search queries? Like this is range search, but
right.
I guess this idea is very general.
Right. So we have only scratched the surface on this. For example, we don't know. We try to generalize on range queries, and range queries is really difficult. There's a lot of combinatorics that are involved, very interesting combinatorics, and we hit wall a lot of times. So there's a lot of there's a lot of things to be done here, right? And then of course, like you said, right, there is other queries, right? So what happens with k-nearest neighbors, for example? What happens with other arbitrary database queries, right? So what kind of modifications you have to do on the database, on the encrypted scheme, to actually produce a reconstruction space that is big enough so that the adversary cannot really tell what's going on.
All right. Thank you. And just one more question. So in this space of searchable encryption, so to me, so I've read a couple of papers in this area before, and it seemed to me that the whole area is like someone is coming up with an attack, someone is coming up with fixes. This idea seems very general, which seems like there will be a mathematical guarantee. But I assume that there are people working on other kinds of things, like for example, I know there are papers on like leakage suppression, and something as well. What are the other approaches broadly? Like this is like one kind of very mathematical guarantee that you can do, but can you say something on that?
Right. So I think leakage suppression has to do mainly with so one technique that mentions leakage suppression has to do mainly with the search pattern, with concealing the search pattern. And I think this in a sense is a bit more general because it assumes that the worst case. So you assume that okay, you are in a position where you have seen everything, and then you want to argue about what happens next, right? So So right, I mean, so definitely leakage suppression is one other way to address this issue, right? But I would say I think I'm not up to speed, to be honest with you, on leakage suppression, but I believe it has to do with concealing the search pattern.
Good, thank you. So, but would you agree that like at the moment, like this work is like this slide of yours is very promising, but otherwise it seems like things are just broken right now, right? Like
absolutely, I completely agree. And I have worked on searchable encryption for so long. I have worked both on construction and on attacks. And we have to be extremely careful when we use searchable encryption. For some applications, it might be okay, but in general, it's a very weak primitive. And that's why we need to think about, but the question is, you can't have the two extremes where you have like ORAM and fully-homomorphic encryption, searchable encryption. One is completely broken, one is super secure but very slow. I mean, there has to be something in the middle, right? And this is what kind of this new line of work that we're pushing aims to be. Right?
Thank you.
But I completely agree with you that searchable encryption is not a good primitive. I mean, it's an eternal encrypted database. You have to be extremely careful, right?
It seems like a promising primitive with this. So this kind of mathematical guarantee is really good, right? Like if you can give very precisely that.
Right.
Sorry, one last question. When you're testing this, do you make assumptions about the number of queries that you have? Because for example, it seems like if the number of queries is like very sparse, then it should still be good, right?
So we have here, if you see Andrew, we have here the domain is N is 1000. So this is the domain of the database, and Q. So we're using around 10,000 queries here.
I see. So here for the size 1000 database, if you have less than 10 to the 4 queries, does it just not work as well, or?
Yeah, of course. As you increase the number of queries, you will get better results. I'm not sure whether we have results with less number of queries. I have to look at the paper, but maybe we have at the paper. Right, so here's the answer that I put. But of course, right, if you have less queries, the estimations are not going to be good, right? So,
have you looked at sort of mathematically looking at like the lower bound of queries in terms of like N and some like security parameter? Or
that's very interesting. That's very interesting. There are some mathematical bounds, I believe, in these papers. Right. So, but we haven't really taken this theoretical approach. But definitely, we might be able to construct an estimator specifically for this problem. Pretty much here we just use it black box, right? But potentially, if you specialize it, you might be able to get something better and actually prove some bounds. Right?
Yeah. No. Yeah, that's interesting.
Yeah, to me it was really interesting that these techniques exist. I mean, I didn't know. I just learned this jackknife estimator, right? That you can kind of observe samples for distribution, and you can, without any knowledge of distribution, to kind of estimate the support size, like how many elements right, are in the distribution. That was extremely interesting. Right.
And then here, when you choose the queries, are you just choosing queries randomly, or?
Right. So here in this plot is uniform query distribution, right?
Oh, right. Okay.
This uniform. In these other plots, they follow these distributions which are not uniform, right?
Okay.
Okay, if there are no other questions, let's thank Professor Papamanthou again. That's really a good talk.
Thank you very much. I really enjoyed talking with you. Okay.
Thank you so much.
Thank you very much. Thank you.